Okay, so yesterday we have seen the device structure and the first step. Okay, so if there is no gate voltage is applied, so then it could not form a channel here. It will provide a strong resistance so that there is no chance for current to flow from this region to this. Okay, so that's why very first step in MOSFET operation is you have to apply the gate voltage. Okay, you have to apply certain gate voltage so that, so what will happen, these diodes should be forward biased, and here the whatever holes are there, so whatever p type substrate holes are majority charge carriers, this should be moved from this place to bottom, and there are abundant n type charge carriers, that is nothing but electrons are present in both source and drain this doped regions, so they will be brought into this place and forming a channel now. So since the channel is formed now, so the next step is you will apply a small drain to source voltage. So source is ground, okay, and we'll fix the VG. So VGS, after once we form the channel, so we'll fix the VGS and we'll vary the VDS. Okay, so drain voltage will apply so that slowly current flow will happen. That is called as the drain current. Okay, and as we increase the drain current, so the current.
Sir, we are getting a distorted voice.
Okay, now also just.
Now it's proper.
Okay, maybe a little fast. That's why it is breaking. Just a minute. Okay. So as the electron density increases here, so this will more current will be flowing in this region. Okay. So this same operation we'll be doing it now, and we'll be explaining in the characteristics as well as the equation. Okay. So yesterday I was explaining all these things, the same thing explanation. Okay. So that's why a MOSFET is called an N-channel MOSFET. So since we have formed a channel of electrons now, so in p-type, just a reverse will happen. So doped regions will be P plus, okay, and this is the n-type substrate. So we'll move the electrons to downwards, and the holes will be placed over here, and we form a p-type channel. Okay, so that is the difference between n-channel MOSFET and p-channel MOSFET. Okay, so this channel is created by inverting the substrate surface from p-type to n-type. So the substrate, the p-type substrate only, some portion we have inverted into a n-type. That's why this layer is sometimes called as inversion layer also. Okay, so that was the discussion. Creating a channel for current flow is the second step. Nothing but booting your device, okay, for the further conduction. So the value of VGS, so I applied here gate voltage, right? So I will be slowly applying the gate voltage to form a channel. The value of VGS at which a sufficient number of mobile electrons accumulate in the channel region. From doped N plus region, we try to bring the electrons to that channel place. Okay, so how much voltage, as we slowly like 0, 0.1, 0.2, 0.5, like that, we'll try to increase the VGS value. Once it is formed a complete conducting channel, so that voltage, at what voltage that forms a conducting channel, no, that we call as the threshold voltage. So this is denoted as VT. I earlier mentioned it as thermal voltage, so correct it, it is a threshold voltage in MOSFET. Okay, and it is denoted as VT. Okay, so that is the indication. So threshold voltage VT. So this one parameter we understood now. Okay. So length we have understood, width we have understood, and also thickness of the oxide layer understood last class. Now this is another parameter. Okay. So VGS is the input voltage. Okay. So this voltage when forms a conducting channel in the p-type substrate, so that voltage we call it as threshold voltage VT. Okay. So obviously VT for an N-channel FET is positive. So N-channel MOSFET, it will be positive, and P channel, it will be negative value. And that value of VT is controlled during the device fabrication. Okay, so fabrication time, they will control that. And its value normally in the 0.5 to 1.0 volt. This is there every device. Okay, in the diode, you had the cut-in voltage of 0.7 for silicon. Okay, and for transistor BJT, you had a VBE, base to emitter voltage of 0.7. Okay, for a transistor. So same way, here we call that as a threshold voltage to form a channel. Okay, so that is 0.5 to 1 volt here. Clear? So then the gate and the channel region of the MOSFET form a parallel plate capacitor. Okay, so in the diagram, If you see, so this is the oxide layer here in between, and above this portion is gate, and below the oxide layer you have a channel now. Okay, N channel is there. So now this middle portion forms a capacitor. Now it looks like a capacitor formation. Okay, with the oxide layer acting as the capacitor dielectric. So this oxide layer will act as the capacitor dielectric. So this is the equivalent we are making. Okay, the positive gate voltage causes, so gate voltage we have applied positive. This causes positive charge to accumulate on the top plate of the capacitor. Okay, so that means gate electrode. So when you apply positive, so here every positive is there. Okay, all positive electrons are there. So that's why whatever positive was there in this side, p-type substrate, they are repelled to downwards, and the n plus regions electrons are accumulated near the surface here like this. So now this is a perfect capacitor formation. Okay, the corresponding negative charge on the bottom plate is formed by the electrons in the induced channel. Okay, an electric field thus develops in the vertical direction. So electric field will occur in this direction, and it is this field that controls the amount of charge in the channel. So how much charge should be there, this field it will be. So that's why another name come now. Okay, MOSFET, metal oxide semiconductor structure, field effect transistor. So the field effect is forming here. Okay, due to this capacitance. Okay, so it is this field that controls the amount of charge in the channel, and thus it determines the channel conductivity. Conductivity means what? Flow of electrons. Okay, in turn the current that will flow through the channel when a voltage VDS is applied. So next, what is the step? So channel is formed now. So now we are slowly applying a VDS. That is the third step. Okay, so when we apply a VDS, so applying a small VDS now. Okay, because channel is formed now. So now we start conducting the channel. Having a induced channel, now apply a positive voltage VDS, drain to source. Source is grounded, so drain voltage we are applying. Okay, similarly gate voltage we applied, source is made ground, VGS we called, right? So that is input voltage and this is output voltage. Okay, between drain and source, so we'll apply the VDS between drain and source, and we first consider the case where VDS is small. So another case we'll consider large VDS. Now we'll consider small VDS, value of 50 millivolt or approximate. Okay, the voltage VDS causes a current ID. Okay, the channel is formed now. In that channel the electrons will flow now. So that flow or conductivity we call it as current ID, drain current, to flow through the induced N channel. Current is carried by free electrons traveling from source to drain. Okay, hence the names source and drain. By convention, so it is source to drain, meaning here source is drain here, so draining at the source side, the ground side. Okay, so that's why the name. By convention, the direction of current flow is opposite to that of the flow of negative charge. So as the electric field direction is vertical. Okay, vertical in the sense source to drain is there, but the direction of current flow is opposite to that. Okay, so normally conventional current is opposite to that. That's why. Thus, the current in the channel ID will be from drain to source as it indicated in figure. The magnitude of ID depends on the density of electrons in the channel, which in turn depends on the magnitude of VGS. So how much? So this current ID depends on density of electrons in the channel, and this in turn depends on the gate voltage what you have applied. Okay, and the threshold voltage. Okay, so approximate that. Specifically for VGS equal to VT, that is the threshold voltage, the channel is just induced. So just if we apply VGS approximately equal to 0.5 to 1, so channel is formed. But if you still increase the VGS value, the current conducted is still negligibly small. Okay, so as VGS exceeds VT, we could not increase the VGS beyond VT. So if you do that, more electrons are attracted into the channel, and we may visualize the increase in charge carriers in the channel as an increase in the channel depth. Okay, so in between instability is there. So this results in a channel of increased conductance or equivalently reduced resistance. So in fact, the conductance of the channel is proportional to the excess gate voltage. So all these terms you will understand when I draw the characteristics. Okay, so the VGS. So this is another term we are going to discuss here. So threshold voltage understood previous slide. Now this is excess gate voltage, that is VGS minus VT. Okay, so it should be always positive. So VT should not be more than VGS, and this is called as the excess gate voltage, what you are applying for more conductivity. Okay, I'll continue this. Okay, So this is the channel. Okay, so channel formation, and we have applied a small VDS of 50 millivolt here, and this is VGS. The current is 0 here. Okay, and this IS, the source current IS is all equivalent to ID, because this same current only coming over here. That's why, as in BJT, bipolar junction transistor, you had a collector current and emitter current, some concept, and base current, right? So in this case, the base current or gate current will be normally 0, and whatever drain current is there, which is equivalent to source current. Okay, that's why we'll not have any term like IS. We'll not write it at all in MOSFET. So at the source as well as drain side, we'll show the same current ID. Okay, that we'll see in MOSFET biasing and all. Okay, so that's why focus on this part. So if you require, I will send the notes also of this to read out. Okay. So known as the effective. So I told you excess gate voltage, no? So it has other names also called as effective voltage, okay, or overdrive voltage. So this is the term normally we'll use, overdrive voltage. It follows that the current ID will be proportional to VGS minus VT, and of course the voltage VDS that causes ID to flow. Okay, so at the gate side we have to maintain this condition. If you exceed that, we call that as overdrive voltage, and VDS, small VDS we are applying, which will cause the current to flow. Okay, so this is about the third case of operation when we apply the small VGS. So now we'll sketch this. Okay, so we got the output now, ID current, and VDS is the input. So you can sketch it for various values of VGS. So VGS value, we keep it 0.5, 1, 1.5 as we increase. So what will happen to the current? Okay, and we observe that the MOSFET operating as a linear resistance whose value is controlled by VGS. That's why the resistance is infinite for VGS less than or equal to VT. So if you does not apply the VGS equivalent to VT, what will happen? The first case, high resistance will occur. So if you apply the VGS approximately equal to VT, a channel will be induced. If you still increase the VGS, that we call it as overdrive voltage. So then current conduction will be more, and it will act as a linear resistance. Okay, linear characteristics it will show. So that only I will show you now as a diagram. Okay, the characteristics. So okay, so these are the characteristics of the MOSFET. Okay, the VI characteristics we say. So this is the output current ID in milliamps, and this is the voltage VDS in millivolt, and the controlling parameter here is gate to source voltage. The same characteristics you have seen in BJT case also. Output you had the collector current, right? IC. The input is the base current, right? So input is the base current, sorry, base no. Here output voltage we have drawn VCE, right? And the controlling parameter was the IB here. So IB value in microamps we have given some values, and you have seen the characteristics. Okay, so that's why BJT is called as a current control device, because IC depends on beta times IB. So that's why it is current control. But whereas MOSFET, here the output current ID is depends on the input voltage VGS. That's why it is called as voltage control device. Very first I told you what is the difference. Okay, that is because of these characteristics. So now if we apply VGS value less than VT, your MOSFET will not be on at all. So this is at the 0 position. We call it as cutoff region. Okay, the diode will be in off state. When you apply a VGS equal to VT plus 0.5, that is above the VT, right? So threshold voltage you have applied. So then it will start conducting, and small current ID will flow linearly. Okay, so as we increase the VGS now, so VT plus 1 we have applied, so current will increase. So VT plus 1.5, still current will increase. Okay, VT plus 2.2 volt, so current will still increase. So like that, the increase in current you can see, and at some instant you can see the linear increase in current also. That should not happen. So that case also we'll consider now, that is large VDS. Okay, so how much we can apply large VDS? Okay, at what extent we can apply? Okay, so from this, the description we indicate that MOSFET to conduct, a channel has to be induced. So just to summarize this so far, and why it is called as enhancement MOSFET. Okay, so then increasing VGS above the threshold voltage enhances the channel. Okay, so first we have formed channel formation, then applying the VGS, more value of VGS, we try to enhance the channel. That means expand the channel. That's why this MOSFET is called as enhancement MOSFET. Okay, or it is enhancement mode operation we call, or it is enhancement type MOSFET. So now we have understood this. Okay, why it is called enhancement. Then why it is called metal oxide semiconductor? It is because of the device structure. Metal is gate electrode, oxide layer is there, and below that you have the semiconductor. Okay, so it is having p-type, n-type, everything there. And then FET, so the capacitor formation, field effect occur there, field effect transistor. That's why it is in single term, it is a transistor. So BJT is bipolar junction transistor, and it is metal oxide semiconductor field effect transistor. So this is the name how you got. And finally, we note that the current that leaves the source terminal is equal to the current that enters the drain terminal. So this ID is always equal to IS, and the gate current IG is equal to 0. Normally, IG current is 0 in the case of Mosfet. Okay, and we don't have a term like IS and all. We will not write it at all. We'll say because one notation will be reduced. So same ID will be shown at the source side. Okay, that we'll see in Mosfet biasing circuits and all. Okay, so once I cleared this Mosfet characteristics, no, although I have took 2 classes extra, so it will benefit me more. Okay, so when I am explaining this part in next and the second module also. Okay, so that's why carefully go through this. Okay, so don't neglect this. Okay, not there in syllabus means not studying. No. Okay, I'm just revising it, whatever you have done in there before we go. Okay, so next last operation is we will increase the VDS value now. Small VDS applied previously. Now we'll try to increase this. For this purpose, let VGS be held constant. Now VGS could not be altered now. Okay, both we are altering VDS as well as VGS, means a conflict will occur. So that's why we'll keep a VGS which will be a value greater than VT. We'll fix it. Okay, VG value will fix it. Only VDS value try to change it. Okay, so VDS appears as a voltage drop across the length of the channel. So that is, we travel along the channel from source to drain. The voltage increases from 0 to VDS. Thus, the voltage between the gate and points along the channel decreases from VGS at the source and to VGS minus VDS at the drain end. Since the channel depth depends on this voltage, we find that the channel is no longer of uniform depth. Rather, the channel will take the tapered form. Okay, so this is the thing I wanted to tell. So tapering shape will form. So because of this, what will happen? Deepest at the source side, it will be deepest. Source means at the drain N plus, and shallowest at the drain end. So drain end, it will become a small.
So your voice is literally coming distorted.
Yeah, in between it is happening. It will automatically get correct. Now it's okay.
Yes, sir.
Okay. So as VDS is increased, the channel becomes more tapered and its resistance increases correspondingly. So because whatever channel formed earlier, that channel now try to break up. Okay, so that is the thing happens. And I will show you this with a diagram so that you will understand. So that's why you have to apply the VDS in a limit. Okay, so that it should not break the channel. Okay, so this is the thing will happen. See here. Okay, so VGS is fixed now. Okay, and we try to increase the VDS value slowly from small value to larger value. Slowly what happens? So this whatever channel was there expanded. So it will try to be shrink at the source side. Source side means it is a coming side. Okay, that is the drain. Okay, and drain terminal. And finally it will take a shape like this. So there is no channel to current to pass at all. So it will get a saturated or constant current it will come. Okay, so that's what I told you. So it will be keep increasing, but after some extent, okay, some extent of VDS. So this will show you this tapered shape. Okay, so that is the fourth step of operation. So initially VG does not apply. So both are reverse bias junctions. Then applying VG, a channel is formed. Then a small VD is applied. So current ID is try to flow. Now as we increase the VDS, it will try to break this channel into a tapered shape. Okay, so this is the 4-step explanation of the characteristics. Okay, so this is the curve showing the regions now, as we have seen in transistor, cutoff, active and saturation region. Similarly in Mosfet. Okay, so this is the VDS here applied, and this is the output current drain, and we are applying the VGS, which is greater than VT. Okay, and this is called as the VDS saturation value, that is equivalent to VGS minus VT value. Okay, so what happens here is initially almost a straight line with a slope proportional to VGS. When you start applying the VGS plus VT, initially we have seen, no, it is increasing, like that curve you have seen. So like that, it will start increasing. But curve bends because the channel resistance increases with VDS. As we increase the VDS value, so as we increase the VDS value, so what will happen? Channel resistance, so it will take a tapered shape. And when it reaches the saturation of VDS value at this point, so it will almost constant, that it will take complete tapered shape. The current saturates because the channel is pinched off at the drain end and VDS no longer affects the channel. So that channel will be breaked there. It will take a V shape, I told you, no? So that will happen at this point. Okay. And this is region, we call it as VDS, which is less than VGS minus VT. We call this as triode region. Okay. So the names in the, this one, Mosfet is either only to triode region and saturation. So this saturation region where VDS value is greater than VGS minus VT and the current is constant here. Okay. And this is the region we'll be using it for our application. Okay. So this is the active region, okay, of the MOSFET. Here. So that's why to make the MOSFET working, we have to apply this voltage to on, VGS minus threshold voltage, okay, or VGS equal to VT. So that voltage, it will make the channel on. So after that, whatever current comes, so linearly you can use it for any application. Okay. So how much time I have? So little 15 minutes time, I think. We'll try to cover the equation parts also. Channel at the drain end to VT. So this is the pinched off, same thing. Okay. Saturates and MOSFET said to have saturation region and the lesser region. So that same explanation is there in this. So I will not go further. Okay. So this is the thing, how it will channel will happen here. Okay. So VDS is initially 0. Okay. So VGS we have applied. So it will be uniform channel, source side and drain side. Okay. As we increase the VDS, so finally it will take a pinch off and there is no path for electron to flow from here to this channel. Okay. So at that time, the drain current will become constant. Okay. So that is this idea. I hope you have understood this MOSFET characteristics. Okay. So keep it in mind. So now what is my intention was to show you that equation. Okay. How it came, that ID VDS relationship. Okay. You can go through this. It is available. I told you, but I don't know. You didn't understood, I think. I took it away. Okay. So the description of ID characteristics will be shown with the MOSFET, okay, structure here. The gate and the channel region form a parallel plate. This also I explained there. Okay. And the same thing we are using here, which the oxide layer serves as the dielectric. If we write the capacitance equation, capacitance per gate area is denoted as COX and the thickness of the oxide layer is taken as TOX. So then we can write the capacitance as permittivity by thickness. Okay. So this is from your basic physics, I think. Okay. So this equation comes, EOX is nothing but the permittivity of the silicon oxide, which is given as 3.9 epsilon naught. Okay. Epsilon R into epsilon naught. So 3.9 is epsilon R, relative permittivity and epsilon permittivity. Okay. So network problem is there. Fine. So this applied. So you got this much value, 3.45 into 10 to the power minus 11 farad per meter. The oxide thickness is determined by the process technology. So it is not you are varying. So it is how it is manufactured. Okay. Different MOSFET will have different values and its range we have seen 2 to 15 nanometer, right? For example, if you take 10 nanometer, then COX value will be this much. Okay. Or it will be this much. Okay. So a microwave also, this can be expressed. So this is one of the parameter we have seen. Okay, COX, epsilon x, K dash we have seen in the equation. So that K dash comes from all this only. Okay. Then capacitance of this strip is given as COX WDX. Okay. So I will show you that figure. Otherwise you will not understand how I am taking all these things. Okay. So this is the picture of the MOSFET I have taken. So this is the oxide layer here. Okay. And this is the gate electrode. Okay. And here you have the distance. Okay. So, and this is the width and then the length of the channel. Okay. So width and L it will come. So here channel. So these are all physics terms. Okay. So capacitor of value COX WDX. So this complete one portion, it is oxide layer. Okay. And that oxide layer thickness is TOX. Okay. So channel and then velocity. So velocity considered as x by dx by dt. Okay, so this distance by time. Okay, so the electron distance, how much travel it from drain to source. Okay, so this is also shown here, dvx by dx. Okay, so all this will be used to derive the this one, okay, equation. So now we'll write the dq, charge, okay, electron charge dq in the infinitesimal portion of that channel. Okay, so that we give it as minus cox w dx into vgs minus v of x minus vt. Okay, so that is v of x, it is shown in this diagram here. Okay, so this is the v of x, it is the difference of that v of x. Okay, so by taking some portion, we try to derive the its drain current. Okay, so how much drain current is there in that portion? Okay, square some size. Okay, so that size we have considered. Okay, the voltage vds produces an electric field along the channel in the negative x direction. Okay, so since we have taken here, direction is this way, right? But normal electric field is opposite, right? That's why while considering this side, I have taken minus sign here. Okay, if you have shown the direction this side, it is plus. Okay, this is dvx by dx. So then electric field E of x. Okay, the electron charge dq to drift toward the drain with a velocity dx by dt. So dx by dt if I take, so it will be given as mu n into E of x. So it is mu n dvx by dx. From this E of x I have substituted here. Okay, so now mu n is the mobility of electrons in the channel. Okay, so the resulting drift current I can be obtained as dq by dt. So you know current is nothing but rate of flow of charge. So now dq by dt can be written as dq by dx into dx by dt. So I have dq by dt here. So dx term is there here, dq by dx. So this dx I will take in denominator. Whatever term remaining I will write there, multiplied by dx by dt. So this term also I will multiply there. So then your equation looks like this. Okay, so all the terms minus mu n cox w vgs minus v of x minus vt dvx by dt. Okay, so now it is in x form. So the current I must be constant at all points along the channel. So what we have to do? So we have to take the differential term. Okay, so you have to apply the integration here to get the limits, apply the limits and get the value, final value. Because here v of x term is there, we have taken for certain portion, right? For that we have to apply the limit, that is nothing but the aspect ratio, w and l we have to substitute. So then mu n cox w, okay, vgs minus vt v of x dvx. Okay, so this dx I have taken this side. So now both side, if we apply the integration from 0 to L, that is the length of the channel, right? In that channel, we have taken small portion now. So that's why if we take the full portion 0 to L, if limit we have to apply. For V of 0, it is 0. And for V of L, it is VDS. 0 to VDS, current is changing. And X is changing from 0 to L. That's why 0 to L ID into dx. And here 0 to VDS will apply. Okay. So if you do the integration, in the books, they have not shown the clear steps. Even this step also, it may be confusing. Don't do that. So you take this equation and you integrate it. So what equation you will get here is, so it is ID you will get here. Okay. And here mu n cox w by L you will get. And here VGS minus VT into VDS minus 1 by 2 V square VDS square. Okay. So this is the term you will get after applying integration. First we'll do and then apply the limits. Okay. So I will not take the derivation. It is not concern, but how it came the equation only. That's why I'm not stressing much. Okay. So finally, so the expression. Okay. So when we apply VDS equal to VGS minus VT. Okay. This VGS minus VT is nothing but VDS saturation, right? So if we apply that, so it is VGS minus, came back. It is VGS minus VT square, we can write, substitute that. Okay. So these are the two expressions are there because there are two regions are there in Mosfet. One is triode region and one other is this one. Okay. So here some of the parameters, the mu n cox is there in here. Okay. And this is normally called as a constant determined by the process technology. It does not depend on you. It is not a variable parameter. That's why it is known as the process transconductance parameter. And normally it is denoted as Kn dash. Okay. And that's why Kn dash will come. Okay. Which is nothing but mu n cox. And W by L is normally called as aspect ratio. Okay. So if you substitute this Kn by W by X, the final equation, it is like this. So you'll be having two equations at the triode region. This is the equation. Kn dash W by L, VGS minus VT VDS minus 1 by 2 V square VDS square. This is for triode region. And saturation region, what happens? So this VDS current becomes VGS minus VT. So that's why, so this current minus 1/2, it will become VGS minus VT whole square. So this is the equation I was using frequently in our MOSFET discussion. Okay. So to bring this discussion, I have done so much explanation. So what is device structure? What is MOSFET operation? What is its characteristics? And how you get this equation? So now at least something you know. Okay. So what is VGS minus VT? So it is VT is threshold voltage to make the MOSFET operating. Then if we have V threshold, overdrive voltage, VOV. Okay. So we'll denote it that. We'll be using that in problem and all. Okay. Then W by L is the gate or channel width and length. Okay. Then K and dash is nothing but the process transconductance parameter given as mu n into COX. Okay. Why capacitance part will come? Because it will form a parallel plate capacitor in the case and electric field exists there. Okay. So because of all, you got these terms. Okay. So it is normally not an easy equation like in BJT. BJT it is IC equal to beta times IB. IB will be given from some resistance formation, VBB minus like that. Okay. Here it is not like that because there are many process parameters are there. Okay. Process transconductance parameters are there. That's why. So this is a simplified form. If you remove K and dash, you can substitute this one, mu n COX. So this is the thing I wanted to explain you. Okay. So now you can easily consider the MOSFET biasing part. Okay. So then you will clearly understand this. So whatever.
Sir, can I ask a question out of syllabus? Like not.
Yeah.